Hello, this is Professor Kuehn. In my last lecture, I spent some time talking about the pendulum. That's a very nice system for understanding the distinction between kinetic energy and potential energy, and both of their link to the concept of work. Work is a central organizing concept that Helmholtz talks about in his book on the conservation of force. So just to remind you, when an object is in motion, as an example, if a bullet is in motion, it has the ability to do work in giving up its velocity. So if it has a velocity v and a mass m, then the amount of work that it can do in coming to rest is 1/2 mv squared. That is sometimes now called the kinetic energy, or the energy within the object by virtue of its motion. And that energy is manifested in an ability to do work. The other kind of energy we talked about was potential energy. This is an energy associated with the configuration of a body or system of bodies. So an example one might give is if you have a mass sitting on the floor and you lift it up onto a shelf, you have to apply a force to it in lifting it up to some height. And then one would say that the potential energy of that system has been increased. That is, you've separated the object from the Earth by an additional distance of h. And so the Earth and that object are in a state of heightened potential energy. That is, they can, in allowing that object to fall back down to its original height, one can recover the amount of work that it took to lift it up to the higher height in the first place. Now, after having talked about the pendulum, Helmholtz also talks about other ways that potential energy can be stored apart from lifting an object upwards. The first example that he gives is the example of a drawn crossbow. And I believe this is on page 116. He says, if I stretch a crossbow and afterwards let it go, the stretched string moves the arrow. It imparts to it force in the form of velocity. To stretch the cord, my arm must work for a few seconds. This work is imparted to the arrow at the moment it is shot off. Thus the crossbow concentrates into an extremely short time the entire work which the arm had communicated in the operation of stretching. The clock, on the contrary, spreads it over one or several days. In both cases, no work is produced which my arm did not originally impart to the instrument. It is only expended more conveniently. In the case of the crossbow, the potential energy is said to be stored as elastic potential energy. How much potential energy is stored? Well, however much work it took to draw the bow back in the first place. You have an opportunity to work on an exercise like this. Exercise 10.3 allows you to calculate the potential energy stored by a drawn crossbow. The next example that he gives is the example of compressed steam. He says compressed steam also has potential energy. How much potential energy? Well, however much work it took to compress it in the first place. So if I might draw a picture here, you might imagine that one would have a piston, something like this, and inside of that one, well, I guess that's a canister, and there's a piston that might be fitted into this canister nice and tight so that whatever gas is contained on the inside is not allowed to leak out. And if one, let's suppose that this piston has a cross-sectional area of A. Maybe it's 1 square inch. Now, if we apply a force to the top of this piston, and in so doing, move the piston down, so if I apply this force right here to the top, and in so doing, I move this piston down by a distance d, one could calculate the amount of work that is done in compressing this gas. Well, the work would be equal to the force that I'm applying, multiplied by the distance through which I move the piston. Interestingly, we can do a little bit of algebra here. We can take force, we can divide that by the area, that cross-sectional area of the piston, that's this A right up here, divide it by the area, and then take this distance and multiply it by the area. So I'm basically multiplying and dividing by the same factor, so I'm not really doing anything here, except I'm making clear that a force per area can be understood as the pressure of the gas, and the cross-sectional area of the piston times the distance through which it moves is the change in volume of the gas in the cylinder. So a pressure times a change in volume gives an amount of work that one must do on this gas. And then once, after having done so, once the gas is compressed, the gas is said to have an increased amount of potential energy, an elastic potential energy stored in the gas, which of course can then be released in expanding the piston. Helmholtz gives a number of examples of how this can be used to drive machinery, and we'll come back to this again later. Another example that Helmholtz gives is the example of gunpowder storing potential energy. In this case, the potential energy is not a gravitational potential energy like it is when you lift a mass away from the Earth. You're storing the work as a gravitational potential energy. In the case of chemical bonds, one stores the potential energy in terms of these chemical bonds. How much potential energy is stored? Well, however much work it took in order to bond the chemicals in the first place. So again, there's this connection between potential energy and work. Tell you what, that brings us to the end of chapter 10. I guess Helmholtz gives a few other examples of applications of this. I think he's very interested in steam and steam engines and machinery, and he spends some time talking about this. But why don't we jump right away into chapter 11 on the conservation of energy. And what I'm going to do is I'm going to begin by just reading the very beginning of this, the introduction, and then the next time we'll talk about some of the content of this chapter. So at the beginning of chapter 11, which I title On the Conservation of Force, I write, in his On the Conservation of Force, the essay Helmholtz wrote, Helmholtz argued that by performing work on a body or a collection of bodies, one can either change its configuration or its speed. In the first case, the work is stored, so to speak, as potential energy. Examples of this are the lifting of a body to a new height or the stretching of a spring. The precise amount of work required and the potential energy that is stored depends on the force which must be overcome in order to change its configuration from an initial to a final state. So think about lifting up a mass in a pendulum clock. In the second case, that is kinetic energy, in the second case the work is stored as kinetic energy. The kinetic energy of a moving body is a measure of how much work the moving object can perform on another object, such as a target, before it comes to a complete stop. Generally speaking, what we today call the energy of an object, or a configuration of objects, is just the amount of work which it is capable of performing. Moreover, and this is Helmholtz's main point, this quantity of work seems to be conserved. When work is done on an object, the object can in turn do precisely the same amount of work on another object. This is what Helmholtz means when he says that the quantity of force which can be brought into action in the whole of nature is unchangeable and can neither be increased nor diminished. So thus far, Helmholtz is focused on mechanical systems, such as water wheels, pendulums, windmills, pulleys, and levers. Now, in the remainder of his lectures, which I'll be talking about in chapter 11 here, in the remainder of these lectures, Helmholtz generalizes his previous analysis to consider steam engines, chemical affinity, batteries, and electrical machines. As we study this text, see if you can detect any flaws in his reasoning, specifically what experimental observations might falsify Helmholtz's new universal law of nature.